Hey guys, today we're going to talk about VESPR theory. Now, VESPR theory is basically the way of understanding the arrangement of compounds, the atoms themselves, and it's explained primarily by the just repulsive behavior of the electrons being not wanting to be near each other. And so let's go ahead and get started. Abbreviated, and I'll recap this later. VESPR is VSEPR. It stands for valence shell electron pair repulsion theory. And so we're going to talk about the structures and the conformations of atoms and compounds that you need to become aware of as you go through becoming acquainted with more molecules. Now, the theory itself assumes that the shape of a molecule is determined by the repulsion of the electron pairs. And so naturally, like I said, you have atoms, they have electrons, they have protons. Electrons don't want to be near each other. Protons don't want to be near each other. Now, they are attracted to the opposite of one another. Protons attract to electrons and vice versa, but not to their same species in this case. So, ultimately, what that does is it contributes to a conformation arrangement based on those bonds. And depending on how much repulsive behavior is exhibited between those electrons, it can form a trajectory or an angle between two bonded species. So let's look at understanding the basic premise of VESPR. You need to understand that it is based on electron dot. Now, electron dot is that kind of arrangement where the dots are representative of the outermost electron valence shell. And it actually is a theory used to predict the shape of the compounds, like we've already said. And it is an abbreviation that's used to represent that conformation. And you want to understand and know that VESPR is abbreviated for valence shell electron pair repulsion. So it's explaining that behavior of those electron shells. And it predicts those shapes based on this repulsion exhibited by the bonds or the pairs themselves. Now, electrons around the central nucleus naturally repel each other, so structures have atoms that maximally spread out because of this repulsion behavior. So let's look at it. Each shape has a name, and we need to become acquainted with these. They include the following: tetrahedral, trigonal, pyramidal, bent, linear, trigonal, planar. And each structure is going to look like this, where you have tetrahedral, you have your trigonal, pyramidal, you have your bent, you have your linear, and you have your trigonal planar. Now, if you haven't noticed, each one of these compounds not only has an original shape, but there's an angle that represents the distance between those bonds. Here it has 109.5 degrees. Here it's a little smaller of 107.5 degrees. This one's not representative or indicative, but we'll get into that. And when it's linear, it's obviously 180 degrees. And then finally, when you have a trigonal planar, it's 120 degrees. And so we're going to look at examples and kind of look at these more in depth if we can. All right, so we have the tetrahedral, trigonal planar, bent, or sometimes called V, the trigonal pyramidal, and then we have the linear finally. And then we're going to talk about each one as a compound. So here we have tetrahedral, represented by the compound methane. As I kind of highlighted before, you have kind of one central atom, and you have four emanating atoms from that. And what happens is, because of the repulsive nature, they form an angle between the compounds where you have 109 found between this hydrogen and this hydrogen. And in actuality, that same angle is the distance between this one and the bottom one, and any of the ones found on the particular compound. And that's your tetrahedral structure. And so there's an even distribution. It doesn't change between them. Maybe it can be slightly adjusted or impacted by what kind of compounds are found to pull or not found. But for the tetrahedral, you have four specific compounds that pull at an even distribution of 109.5 degrees. Moving on, we're going to compare that to another conformation. Now, in that conformation, we're going to look at a practical example of ammonia, where you find less repulsion between the bonding pairs of electrons. So Look at the ammonia. Notice that there are 3 hydrogens that are bonded to the nitrogen, and then it has a lone electron pair. The lone electron pair is the basic electron pair that's not bonded to form any compound. And because they're not bonded, they actually have an impact on the conformation seen in the compound. And ideally, you would think that this and this would have the same angular trajectory because, they basically have the same representative of wanting to achieve octet. However, this one doesn't. It has lone electron pairs that are not present. And because they are present, this is going to impact the angle found between these compounds that are actually bonded in ammonia to the, between the nitrogen and hydrogen. So like I said, in an ideal scenario, the bond angle would be 109.5 degrees, like that with the methane tetrahedral. However, with the ammonia, you actually experience kind of more of a pushing or repelling by these electrons, which cause these angles to be smaller of 107. This is 107 degrees. And so you have that. Now looking at the next example here, this is water. And if you recall from the images before, water actually assumes more of a bent or V conformation. And that's because you have 2 sets of lone pairs. You have both of those electrons. And for some reason, these electron pairs have so much repulsive nature that even though one would expect them to behave similarly and have 109.5 degrees of angle of separation, the repulsion experienced by these lone pairs actually causes this to kind of decrease and form an angle of 104.5 degrees. So looking at them comparatively, this has 109, 107, and 104.5. So it decreases with the addition of the electron lone pairs. And so kind of looking at these structures, one of the things that is oftentimes done in chemistry world is they represent depth of the actual angles. And if you notice, there's a dashed line here, and then there's kind of a widened, darkened line here between these hydrogens. Now these hydrogens are planar. They're lined with the trajectory of the screen, but these represent kind of hydrogens leaning backward and leaning forward, where this hydrogen is going forward towards the screen, kind of right at you, if it could represent that, and this one is leaning more back. And they're drawn to represent depth. And so you want to kind of think about that when you're thinking of the structures. So here, that hydrogen is represented here. That hydrogen is represented there, and it shows that hydrogen going back to maintain having depth. Same with this one, where this one represents the front-facing hydrogen, and this represents that back-facing hydrogen. And so with bent or V, you don't have the same thing because you have the 2 unpaired electrons. They force them to bend, and they're more of a planar arrangement with each other. And so let's go ahead and look at those compounds we talked about before, methane and ammonia. Now the Lewis structure is going to look like this, where we have our carbon with the hydrogens emanating. The number of electron pairs, there's going to be a grand total of 4. So pair here, pair here, pair here, pair here. And so the shape that forms from this is going to be your tetrahedral. And you want to know that because tetrahedral implies this 109.5 degree angle of separation between the bonds. Next you have ammonia, which we represented here in the Lewis structure. Looks kind of like this, where you have your lone pair and you have your 3 hydrogens. Now if you recall, the number of electron pairs here is going to still be 4. However, there's one that's just basically not bonded. And so the actual conformation or shape that's formed is more of a trigonal pyramidal, like we've already talked about. And this angle is impacted where you have 107 degrees of angle of separation between the hydrogen atoms, impacted by these nitrogens having so much need to occupy space that they push the angles of those hydrogens inward a little bit. And so moving on, we have our water and carbon dioxide. Water is going to be kind of our linear structure that we've already seen. Now the number of electron pairs is still going to be 4. The shape, however, is going to be more of a bent or V, and we have 2 paired, 1, 2, and 2 unpaired, or 2 lone pairs. So lone just means unpaired. And our angle, once again, is 104 degrees of separation between all hydrogens. Moving down to CO2 or carbon dioxide, the Lewis structure looks a little bit more linear, and that's actually the shape it goes for. Here for the carbon, you actually have two electron pairs, one and two, and that's because there are double bonds there. There's two areas, and then for those, the shape that it assumes is going to be linear. And so we've kind of talked about those, and hopefully we understand those structures and their arrangements. These are going to be popular in conformations and understanding the arrangement of molecules. And you'll want to be familiar with the angle between the bonds. Let's look here at the next one. And so here we have a beryllium and centralized with two chlorine atoms located on the side. Now, I don't know if you can see this, but there are only two electron pairs here represented. There is two. There are no unbound, no unpaired electrons for the beryllium. And so that means the angle is 180 degrees. Consequently, that would suggest a linear model of conformation of arrangement. Now BF3, you have a boron with three fluorine atoms emanating outwardly, and they have an even shape. That angle trajectory is going to be roughly 120 degrees. There's going to be three of these electron pairs, so to speak, and you're going to want to know that that is going to be your trigonal planar. Trigonal because there's three, and planar because they're all on the same plane of paper. They're kind of a 2D conformation, if you will.